Hi everybody, my name is K.M. Prasad. I have been with integrated engineering software for the last 30 years, and I'm the original developer of this program AMPERES, three-dimensional magnetics. And in this webinar, we will see how an MRI superconducting magnet is shielded. That is the aim of this seminar. I hope everyone is able to listen to my audio. Okay, now I will start the show. So I could, okay. This is the AMPERES program. In this program, we will model right from the scratch how to model a superconducting electromagnet. For this, what I do is I will take one file here. Okay. Okay. So this is a starting file. I take it. Here, the units I selected centimeters, and we can change these units at any time you like. Right now, I will set it to centimeters. Next, this X, Y, Z coordinate system, I have drawn it beforehand so that it will give a good reference for us. And these 4 lines I drew it here is for to develop this the cross section of the electromagnet. I pre-drawn it so that my the demonstration will become simple. Here, first what I do is here I will linearly sweep this segment 0, 0, 0 reference point 0, 0, 4.3 centimeters. Okay, I'll put it this way. That is the first cross section of the first coil, then the second coil. Okay, 4.203. Okay, and this is 0, 0, 0, 6.707. Then this one 0, 0, 14.015. Okay, so these 4 surfaces, they make the cross section of the coil, and this electromagnet, it has got a total of 8 coils. Right now you are seeing 4 coils. The same 4 coils will be present here. We will take it as a mirror afterwards. Let me do this circular. Okay, I'm doing the circular sweep of these 4 cross sections. About the z-axis, like this is the axis, and I'm sweeping it for 90 degrees. So this is the a part of the coils. See here in AMPERES program, it is important any volume that carries current, it should have just 6 surfaces. For example, you observe this piece of coil, this volume, it has got 6 surfaces. This is the surface number 1, 2, 3, 4. Similarly, on the other side 5, and the bottom 4. Okay, bottom 6. The 6 surfaces are there. See, that is a must. Whenever you want to assign a current to any volume, it has to be 6 surfaced. That is the reason why I swept circularly for 90 degrees. I could have swept 180 degrees, but there is a purpose why I put only 90 degrees. You will be understanding once I complete the problem. The next thing is we have to assign currents to this. physics, volume current, assigned from N. So this is the thing. So 1 minute. Okay, see here also what we are assigning is amp turns we are assigning. This is the number that is 3.7839 10 to the power of 5 amp turns. That number I meant through this surface this current is entering, and now the program is asking enter the total current or amp turns. So here we don't do turn by turn, we don't do it. Everything is through that cross section. We'll specify the amp turns. You can see here now that is the current. The next, this volume, okay, this is the amp turns. Copy. Okay, through this surface. Okay. Next, this one. This is 1.37 10 to the power of 6. These are all huge current. That's why these coils are made up with a special kind of material which can withstand so much current. Also some cooling mechanism also will be there. The next, for this volume, the current is in the clockwise direction, whereas the other three they're anti-clockwise. In this case, it is a anti-clockwise direction. Copy. Okay. So this is the surface. The entry surface is that is the surface, and this is the okay. Okay. Now you can see this. These four currents that's sufficient. Other things we can bring it with a computer rotation with copy facility. Now what I do is I will make this as copy on, and also this button I essentially repeat thing. Then you rotate this thing 1, 2, 3, 4. So 0, 0, 0. Z-axis is the thing, rotation axis 90 degrees. Repeat value is 3. So now all the you can see here. So this 1/2 of the coil sections are completed, and if you go and see all the attributes, this volume current attributes, that is complete. See, in our program, whenever you do either displacement or rotation or scaling, any modification with a copy on switch facility, what you can do is in the geometry setup, all the attributes can be to that particular geometric entity that you have taken. It can be copied. See, here I got volume current. So that matters in this case. So anyway, and another thing is for the coils there is no need to assign material, but just for the appearance sake we will use a copper here. So let's make it a block selection 1. Okay, this is a copper coil, and if you see this copper permeability is I took it as 1. It is close to vacuum. So that is the reason why there is no need to assign the material, but for the presentation purpose you can always have material to that. So once you have this, the next step is I have exactly the same 4 coils on the other side of the Z is equal to 0 plane, mirror symmetry. I will mirror this. Okay, take this up. Okay, mirror. Okay, this one. Okay, 0, 0, 0. That is the okay. So that is my mirror plane. About this plane, I'm mirroring it. Okay, you got all the coils system for this electromagnet. Now if you go and see, all the materials will be there. volume currents, volume current. So you can see volume current is there. Now this model is just electromagnetic simulation. Simulation of electromagnet is completed. So better we save this. Save as. I will call this as okay. Let's say show one coils. Okay. Next, what this design has been supplied by one of our customers. His name is Mr. Nick Companion. He's a consultant on the electromagnetic models, and he supplied us. Here, this design is this coils arrangement will produce 1.5 Tesla within something 1 cubic feet centered around 0, 0. That is the aim. We will verify how far it has achieved. To do the one more thing we have to do is you have to assign mesh or elements we call. See here, so this is for this coils you have to assign 3D mesh. This is we got two kinds of 3D meshes, either tetrahedral you can assign or the 3D bricks you can assign. Bricks are a better element than the tet, so I will prefer to use bricks. Bricks here, automatic all. Let's say automatic all. Let's put some 10,000. 10,000. Okay, 3D mesh. This automatic. Now can you see here? This is the 3D mesh, and okay, you take in this. So the mesh is inside these volumes. You can see the lines going inside. It requires only 3D mesh, and the space around this it doesn't have to be meshed, because the analysis, the solver we are using is in our program we got two kinds of solver. One is a boundary element method, another is a finite element method. For this kind of problems, boundary element method is the best suited. That's why you need you don't need any further mesh in the space around this, and you can get the fields anywhere you like. Even after 10 meters away from the coil also you can calculate the fields. That is the specialty of the boundary element technique. Anyway, now let's solve the problem. Run solver. Now you see here, because here this coils, it is a source of current which produces the magnetic field, and it doesn't need, all the currents are well known, so there is nothing to solve. That's why solution comes immediately, instantly you get it. So now I want to see what are the fields in the center in a cubic feet. Okay, let me center. I'm creating a cube here, center 0, 0, 0. 30 centimeters is the side. Let's take this. Okay, in that cube, what are the fields? Magnetic fields. That too, I'm interested axial component, Z component fields. So make it here Z component, and here I want to make it a scatter plot. Let's take a medium volume in a volume. You see in this volume, within this volume, what is my Z component magnetic field? So there is a small variation it looks. Let's put this. What is that variation? Practically this is 1.5. E4 stands for 10 to the power of 4. So this 1.4, that is 15,000 Gauss. So all these colors, they means almost same. The variation part, maybe you can observe here in this place. Can you see here? The variation is, it is slightly 0.15 Tesla less than 15,000, or it is slightly 0.016 Tesla more than 15,000. So it is practically 15,000 Gauss. So the design of this coil system is which is aimed to have 1.5 Tesla. 15,000 Gauss means 1.5 Tesla within 1 cubic feet. Okay, so the purpose is served here. Now what I do is, okay, I will take this plot out, option, delete all plot. Now I want to see along the axis of this, what is the field variation I want to see. So for that, I will draw a, okay, 0, 0, 0, 300. Okay, so 3 meters I'm taking. So let's make this as a graph. Z component, of course, along the axis it will have only Z component. So let's make it just some 500 points. Okay, I select this segment, this one. So start from O, that is origin of this coil. So in this direction I want to draw. The arrows indicates that is in the direction the graph has to advance. Okay, select it. Now if you see here, yeah, it is for up to some particular length, like up to something like close to 40 or 50. Okay, let's see here how much is it? Yeah, 34.2 up to 34.2 mm. It has got one close to 14,995 Gauss. Afterwards it is decreasing. Okay, and at 3 meters away from this coil you got something like 28.9 Gauss. Let's take 30 Gauss. At this place you got 30 Gauss. Okay, now with this so in the MRI applications, this magnetic fields, high magnetic fields, they shield with a metal box around that. So we will go to shielding part now. Just before going to shielding, we will also see what are its contour plots, like within a 3 meters radius. How only we have seen along the axis we have seen here, but the other sides, what are the fields I'm interested to see. So let's make it a contour plot, and I'm interested the magnitude this time. So make it surface. Okay, I will select. Okay, some surface I will select. A circular surface I take it. Okay, this is 300, 0, 0. Okay, 0, 0, 0, 1, 0. So I created a circular surface which is exactly cutting this, okay, whose radius is 3 meters. In this, what are the magnetic fields? Let's take user defined grade, because we'll give a very high fine density grade. So in this 100 divisions, here 100 divisions. Okay, let's see. Okay, let's make it solid color. Okay, now you see here, see this there is, see, it looks like here between these two coils there is a field is going as high as 8.7 Tesla. Okay, so 1.5 Tesla only within that 1 cubic foot volume, but the fields inside here in this color, there's some cyan color here. This color is, if you take something like 3.5 Tesla, it is going all the way to 3.5 Tesla. And near to this coil, it has got 8.7 Tesla. It's such a huge field, and I'm interested to see what are the fields outside. So I will change the user range. I want because these high fields are dominating this the small fields. So I want to see only the smaller fields, like up to something like let's take some 30 Gauss. I'm interested. The minimum is 0.2 Gauss all the way to 30 Gauss. Let's apply say this. So now if you see here, 30 Gauss, yeah, we know that at 3 meters away you got 30 Gauss here. We already seen the graph. But to get 30 Gauss, you don't have to go to 3 meters from the side. It is, I don't know how much this length, maybe half of it, maybe 1.5 meters or 1.6 meters. There itself, we are getting 30 Gauss. These are the two spots, but the rest of this gray color indicates the fields are less than 30 Gauss. Okay. Okay. This is the use of having a contour plot. Now, what we do is, now we will create a shield which is 3 meters by 3 meters by 6 meters. So along the axis, we will put a shield length of 6 meters. Along the cross section here, along the x and y direction, we will use 3 meters. 3 meters square shield we will construct. Okay. Option delete all plots. Now, so what I do is I will create the shield in a separate file and merge the coils and the shield. Then I merge these two files. To do that, I will start with a file 2. I don't want to. Okay, let's save it. Let's save this. Save as. Show. Let's coil. This is solved problem. Okay. Okay, previous one is unsolved, now it is solved. Now I'm taking, this is a file 2. Okay, just only shows coordinate systems. Now, see, the shield 3 by 3 by 6 meter shield with a thickness of the walls and the roof and the floor 1 centimeter thickness. If I create that kind of geometry, it is very difficult for you to observe the mesh and other things. That's why what I do is, first for the presentation purpose, I will make the thickness of these walls of the shield 25 centimeters. I will make it. Once we observe, once we mesh it, then we will scale it. We will make that thickness to 1 centimeter. Okay. Now I'll create the shield. Minus 150 minus 150 minus 300. Okay. X Y. Okay. Minus X Y Z. Okay. That is the baseline for the shield. Then make it linear. Okay. This one. Okay. Okay. Destination X, Y minus Z. Okay. That is the first surface we got. That is the base surface. And here the thickness, I will make it 25 mm for the demonstration purpose. So you take this surface, sweep it linearly, vertical upward, 0, 0, 0, 0, 25, 0. Okay, repeat values. There is something. Okay, this 1 minute. I think I made a mistake. 0, 0, 0, 0, 25, 0. Okay, that is thickness. And now I got the floor of the room, which is shielding the coils. And then I have to erect 4 walls around this. And these walls, once they at the place of meeting of the floor, they should have a common surface. In AMPERES program, when 2 volumes are in contact, those 2 volumes should have a common surface. A unique one, a single surface has to be there. For that purpose, what I do is I will change the top surface here. You will understand once I complete this. I will make this as a stretch facility here. Scale this. So this is the surface. I'm scaling it. but this time I used a stretch, not copy on. It is a stretch. That means that the highlighted surface will scale down, because I'm going to scale it down. The remaining connections, whatever all the connections to that highlighted green surface, they will follow that. Let's see this. 0, 0, 0. Scale factor is 125 by 150 y1, 275 by 300. Okay, can you see here now? Now I made the side surfaces slant, so that the side walls they go and join to this, so that they make a unique or a common surface between the floor and the connected wall. Now next what we do is, you'll make this again copy on, then repeat on. This time we'll rotate. Okay, make it volume. This volume I will take center 0, 0, 0. Okay, that is the axis. About that, so 90 degrees I'm rotating. Repeat value is 3. So now you see here, now I got all the 4 walls for the room. Now I will focus on one thing here. Just okay, I'm hiding that. I did not delete it. So now here you see. Okay, can you see here? So this surface is common to the floor and the back wall, which you are going to create. Similarly, this surface is common to the side wall and the back wall that we are going to create. That is the reason why I purposefully made this the side walls slant. Okay, then okay, again all on. So now we have to make the front wall and the back wall. I will create a linear sweep. So take this surface. Okay, from here to here. So similarly, this one also sweep downwards to close this. Okay, now you got the required surfaces to define the volume, the front wall. I will define the front. Now I define the volume here. So now let's see here. Not the green one, we want the blue one. Control left button. Okay, that's good. Yeah, this is the front wall. This is the wall I want it. Okay, done. Next, we will copy on. Take this out. Mirror. Take this wall and mirror 0, 0, 0. Okay, that's good. That is XY plane. Copy on. So now you got the back wall also. Can you see this? So now you got all the 6 walls for this the room. And now next thing is, we assign the material to this material. We take here material, assign. Okay, make this as block. So all are connected. Things are selected. So now you got a material assigned to it, and the material I selected here 1010 steel. Let's see what is its nature. This 1010 steel, it is a non-linear material. Can you see here the H and B relation in this? For this, it is a non-linear, and this is a first quadrant curve, and it has to pass through 0, 0. And we don't have the Amperes doesn't have the capability to handle the hysteresis. Okay. Now let's save this file. Database, save as. Let's call this show to full room 25 cm thick. Okay, Okay, now this see, please remember that we are going to make the thickness to 1 mm, 1 centimeter afterwards. But for the visualization purpose, it will be easy for us to see this how we mesh for the this problem. So unless we have thickness, a big thickness, it is very difficult to see it. That is the reason why I'm taking 25 mm. Okay. Once we have this, what I do is I take this problem and this file, I merge with coils, unsolved coils. We'll merge with that. Now, if you see, now can you see that the coils are there and this shield is also here, and your currents, whatever currents we have, they are there. Materials are there inside copper, coils made up of copper, and the room is made up of 10-10 steel. And I want to tell you one thing, we got a big library here. So material manager, if you see, okay, let me see here. Okay, model, okay, we got a library here, metals, we got aluminum, iron, silicon iron, 10-10 steel, 10-12, and so many things like here, M19, M36, vanadium thermidor. There are so many kinds of steels. Materials are available. You can use any material, or you can make your own material. You can edit all these points and you can create your own BH curve. Okay, so only thing left for this problem is the meshing part. The meshing in this case, again, this is, for this kind of problem here, we want to find out what are the fields outside this box, and those fields will be invariably very, very small, like 2 Gauss, 3 Gauss, 5 Gauss, like that. But the inside the box, in the coil, we got a huge field like 4 Tesla, 5 Tesla. At the center, it has got 1.5 Tesla. So, so there is a big contrast, high fields to small fields, outside small fields, and that too, this is an open region problem. You suppose you want to see the fields around something 1 or 2 meters away from the room. You can find out if you are using boundary element method. If you want to use the finite element method, what it has to be done is there will be artificial truncation of this region, and also this kind of open region problems, finite element method is not good. It takes too much time, and the accuracy is also, and because we are interested the smaller values of the fields outside, and because once you put a truncation here, artificial truncation of the region around it, and on that artificial truncation, what they do is they put electromagnetic potential at 0, then the fields may not be very accurate what we are calculating outside. So boundary element method is the best method for this application. So so when you are using boundary element method, see the source coil part only you have to use 3D mesh we already seen. On the steel part, you need to assign 2 kinds of mesh, because the reason is the material we have taken nonlinear material. Because it is nonlinear material, in those volumes you have to use 3D mesh. On the surfaces, on the material interfaces, for example, this you take this top surface. This surface, it is a material interface between 2 materials. Below that highlighted surface, it has got 10-10 steel. Above, it has got air. So that surface is a material interface. You have to put 2-dimensional mesh on that. So we will focus now to assigning the mesh on the first 2D mesh, then afterwards we will put 3D mesh in that volume. Let's focus on only one volume. Let's hide everything to make the demonstration simple. So I will take the top volume. Let's see, This is the volume. You see here in this top volume, it has got 6 surfaces. Bottom one, top one, side 4 surfaces. Side 4 surfaces, they don't need surface elements. The reason is because they are interface between same type of material, the 1010 steel. So you don't have to assign the 2D mesh. What I do is I will hide even those surfaces also. This surface, hide it. Okay. Now these are the 2 surfaces, you have to mesh it. Okay. Thing is, these 2 surfaces, one looks big, another looks small, because the reason is the thickness I took it as 25 centimeters. Suppose imagine that if the thickness is only 1 centimeter, I think the bottom surface would be as big as the top one. Okay, so that means whatever mesh we put on the top surface, we can put the same mesh on the bottom surface also. So that is one point. The second point I want to mention in this case is, see here, you imagine that right now you have the thickness of this wall is only 1 centimeter. Just imagine that. Once you imagine that, what will happen is this side here, it is 3 meters, that's 300 centimeters. This side will be slightly less than 3 meters. Actually, it will become 298 centimeters, because 1 centimeter on either side, if you cut it, this becomes 298. This is 600 centimeters, that is 6 meters. This is 598 centimeters it would become if the thickness is 1 centimeter. Okay, then what is how much minimum mesh we have to put? That is the point I want to explain now. Let me go to here to the mesh. 2-dimensional element, we got a triangular mesh and quadrilateral mesh. Triangular mesh, it's pretty like it has got a good convenience, like any shape of surface we can apply the triangular mesh. But the quadrilateral mesh, whenever you want to apply it, it must be 4-sided surfaces. That is, a quadrilateral mesh is a superior mesh compared to triangular mesh. So to get very good values, I want to take a quadrilateral 2D mesh. So here I take assign divisions. Let's take this surface I selected. Now can you see that this blue line, it is asking how many divisions you want to cut it. I want to cut it into 120 divisions. Okay, see, right, it has already cut 120, and now the blue line is here. How many? It has 60. I want to cut it. Okay, similarly go to the bottom surface. So here also, because the blue line, it would have been 298 centimeter. It's same as 300, close to. So same divisions I take 120. Then here also 60. Now if you see the reason why I took that 120 by 60, if you see this, I'm getting a square side of okay, let's put this way. See, each element is a square shape. It doesn't have to be square exactly. The size of the element would become 5 centimeter by 5 centimeter, because 600 divided by 120 is 5 centimeters. Similarly, 60 divided by 60 divided by 30 divided by 60 is 5 centimeters. So this 5 by 5 element I put it. The reason is I have taken thickness as 1 centimeter. The element size must be less than or equal to 5 times this separation of the parallel plate here. If it is thickness is 1 centimeter, the element size must be 1 times 5 by 5, or it should be less. If you want to put more number of elements, it is fine, but the size at least it must be 5 centimeters you should have. And if the thickness is 2 centimeters, so 2 times 5, 10 centimeters. So this is the element can have a size of 10 centimeter by 10 centimeters. In such case, my divisions will be a fewer number of divisions is good enough for me. Anyway, that is the way you have to assign the elements. Then, okay, next on the same top piece, I want to assign 3D elements also. That I will show here. Okay, now 3D elements. Let's see this. I'm going to element. Still, I'm using 3D bricks. Assign uniform. In this case, if you take, can you see here? This is the now highlighted side, blue color. I want to divide 2 parts there. Now this one I want to divide into 60 parts, and this is 120 parts. Like exactly, I'm trying to match with the whatever elements I used on the surface mesh. Same divisions on the surface. I'm on the top of the volume. I'm taking it so that on the surface of the volume, the 2D elements and 3D elements will match. It is not necessary but recommended. So now see here. Now see, this is the 3D mesh. Along the thickness, I divide into 2 parts. Okay, so like that, rest of the other volumes also will be divided. Now what I do is I will take up, I will bring a model which is already elemented in this fashion. I will bring that up on the screen. Okay, so this is a solved problem, a full room. Let's open this. Open. Okay, here. So this is a problem solved. Okay, maybe I should do one more thing here. Okay, I forgot. Okay, let me do one thing. Okay, I told you that I will scale it down, right? Okay, let me open this stuff. I should have done. Okay, full room. You take it again. Full room. Merge with coil. Now, after you put all your elements, what you can do is we will easily okay, we hide this. Okay, hide this. Okay, now what I do is I will scale it up with a stretch facility. So here, okay, scale it. Now you take this surface, this one, 3, 4, 5, bottom 1. So inner box you take it. Okay, all 6 we have selected. Okay, all 6 we have selected here. Now see here. So now I'm scaling it up. 0, 0, 0. Scale factor is 149 divided by 125. 149 by 125. 299 by 275. Now if you see, hold on. Now you see here. Now you hide this part. See now see here the thickness the thickness I will take here. Okay, this part. What is the distance between here to here? The slant distance, and also I will take this and copy, because these numbers are small digits, so you better I will copy onto a paint. Okay, paste it. Now this is okay, 1 minute. See now, see here, the distance, the difference in x coordinate is 1 centimeter, distance in y coordinate is 1 centimeter, z coordinate is 1 centimeter, and the distance is angular, that is a diagonal distance 1.7320. That is the distance. So now this room is walls with only 1 centimeter thick walls. See, all this, what you can do is you mesh everything, then you do the scaling, then it will be your mesh will be, it won't be disturbed. Okay, now I go to the problem which we already solved, full room. Now I will show you the, okay, why not I do this one again now? Database, save as, okay, show 3, okay, full room, okay, show 3, plus coils. Okay, now let's open the solved problem. Full room, okay. To solve this problem, what should be the computer power? Because it is not a small problem. It is a big problem. Let's see. Okay, I'm hiding this. Now you see here solution elements, quadrilateral elements. Okay, let's put this into this. See, now you got here all full-fledged the elements here. Now if you see quadrilateral, see how much problem size, what is the problem size this? So this again is small, it is too small for you to observe. I will copy onto the paint. So let's put here. Paste. Okay, to solve this problem, it has got 72,000 2D quadrilateral elements, and that leads to 148,000 matrix equation, and it needs to solve this problem. You should have your hard disk space must be. While solving this problem, we create 2 scratch files. Scratch file number size would be 325 gigabytes. Scratch file number 2 will be around 85 gigabytes. You should have close to 410 gigabytes of hard disk you should have to solve this problem. And the second thing is, the most important thing is the scratch file number 2. This is the most important thing. See, the speed, how much speed, with what speed we can solve this problem is decided by scratch file number 2. This is 84 GB RAM. If you have 84 GB RAM, AMPERES program will store this scratch file number 2 in RAM, so that when solving the problem, it will be very, very fast. Okay, so what we recommend to solve this problem, yeah, anyway, having a big hard disk is not a big deal. These days 1 terabyte of hard disk is there, but this RAM, to solve this kind of problem, you should have at least 84 GB RAM for this problem, and overheads, let's take another 6 GB, 90 GB RAM you should have on your machine. And also, see, we use parallel processing, so if you have more cores, the CPUs, it is better. On my machine, I got 6 cores I got, so that's why this problem took, let's see here, let's see, this is already solved problem. I'll take this, I will. Okay, this I put onto the paint again. So because we are using non-linear materials, what happens is Okay. Okay. First of all, this problem started at 10:08. It completed at 12:45. So that means it took 2 hour minutes it has taken to solve this problem. This problem, because we used nonlinear material tungsten steel, it is iteratively solved. You see here nonlinear iteration 1, 2, 3, 4, 5. 5 times this problem is solved. Because this multiple times the matrix equation is solved, that's why you should have RAM, bigger RAM. The reason is we are solving problem not once, we are solving it 5 times. In this problem it is 5. In some problems the nonlinear iterations may take 10, maybe 15, maybe 20. So till it gets some convergence, material convergence, it will be solving it. So this problem took 2 hours 35 minutes. So so this problem is solved problem. Now we will see what are the fields in this problem. Okay, we'll do exactly the same kind of analysis. Let's see here. Okay, at the center, by putting a steel room, what are the change in the fields in the center? There will be some change. Let's take okay, 0, 0, 0, 30 centimeter cube. Okay, in that cube, okay, what we do is we'll hide, okay, one of the side wall we will hide it, then only we can see it better. Okay, okay, in this analysis fields, calculate, okay, make it z component fields, not the user range. Let me make scatter plot. Okay, volume. Let's take, okay, let's course is good. Okay, let's take this. Okay, okay. So that is scatter plot. Put scale. Yeah, there is at 14,980, 20 Gauss less, but the uniformity is still there. But there is a 20 Gauss reduction. If you're interested, 1.5 Tesla there. So what you have to do is you have to scale up your currents by 1.5 divided by 1.498. That kind of scaling, if you do it, you will get your 1.5 Tesla at the center. But the uniformity is there. Within 0.5 Gauss, it is the uniformity of the fields is there. Okay, so that is done. Next, okay, delete. Okay, delete all plots. Okay, next, this I want to see what are the fields right on the surface of this surface outside to the air. Okay, let me do one thing. Arrow plot. I want to take it right on a surface. Let's take this here. On the surface, okay, because the fields are discontinuous, magnetic fields are discontinuous on a material interface. That's why program is asking, you want to calculate on the green side or the red side? I want to calculate on the red side because that is the side of the air. So that's why what I have to do is I have to make the red one as green. Control left button. So now it has come here. Now I have to press left button. So let's see. So now you see here. See at the corner, okay, let me do one thing. Option, move scale. Okay, okay. Okay, may slightly make it big so that 3. Scale it up. Okay, these are the fields here. If you see here, the corner has got 87 Gauss because of the singularity, this sharp corner. But somewhere in the middle, you got. I think these blues are anywhere between 30 to 10. Let's do that. So 10. Let's make this is 30. Okay. Oh, 30. Okay, that means okay. Let's make it okay. Okay, 20. Okay. So that is up to here. You got 20 Gauss on the side of the air. Okay, so this is one thing. Now let's see along the axis what are the fields. I want to see that. Okay, delete all plots. Okay, first we'll see around. We will see in a big surface. We'll see that gives a better picture than just only the axis. Okay, let's take this. This time we will take 350 0 0 0 0 0 0 1 0 axis of the circle. Okay, now I've taken this time a 350 radius circle. Let's make it all on. So this is what we have. This is a circle. I want to go and see around this what are the fields. Graph. Let's take magnitude along the segment 500 good. Okay, let's take this segment, this segment and this segment. So start from here. Actually one segment is good enough. This is a symmetric problem. Okay, let's see here. Okay, so here, because we are far from the wall here, you got 1.6 Gauss. Whereas here you're close to and 1.6, start with 1.6. As you go like this here, you're coming to the somewhere here, corner here, the field is going to 38.8. Let's take 40 Gauss. Then in the middle, that is exactly the center of this face here. This is becoming. Let's see here. This is, what is that? Let me see. Okay, 1 minute. Okay, yeah, 12.37 Gauss. 12.37 Gauss in the middle. So that is the thing. And similarly, you can, if you want, you can calculate what are the contours on that circular surface. Let's calculate that also, contours, but it takes a little time. Okay. Okay. Okay, we'll take a simple fine quant. Okay, here it's calculating, because anyway we're interested fields outside mainly. Okay. Okay, inside it has got 3.5 Tesla. It is a coarse plot. You should have a more grid. So outside, let's see. Outside, I want to see. Let's give the 40 Gauss. Yeah, okay, that's good. Now if you see this, so this is so 0 to 40 Gauss, you are getting, that means near to the wall still the field is large. Okay. Similarly here, this part, it has got very small, like 1.5 Tesla, 1.6 Tesla, 1.6 Gauss. So it needs further shielding thing, like either we have to increase the thickness of the walls. That is one technique. By increasing the thickness of the walls, you may not get such a great advantage, unless you increase really big. The best way is, instead of using one layer shielding, if you use 2 layers, then it would be more effective. Shielding will be more effective. See that part, I will touch that part. See, thing is, okay, now delete all plots. Okay, see, plan is this: modify and delete surface. This surface, we don't need it. Okay, block. Okay, similarly, we don't want this cube. Modify, delete. The strategy is this. Like, see, if you observe this problem, we are saying this problem itself is big. It has one single layer itself is, you need to get 90 gigabytes of RAM on your computer. to solve in a reasonable time. If I put another layer which is bigger or smaller, see what happens is the RAM size will become huge, maybe 250 or 500 gigabytes of RAM. It is very difficult. But in this problem, there is a threefold symmetry is there, because this problem is symmetric about z is equal to 0 plane, that is xy plane, and similarly x is equal to 0 plane, y is equal to 0 plane. It is a symmetric problem. See, why not we make use of that symmetry facility? In the AMPERES program, you can make use of the symmetry facility and you can cut down your problem greatly. But still you get the results for the full model. So what I do is I will cut this problem into 1/8 and get the results, and then put another layer to this, and we see the effect of the double layer shielding. Now modify, delete volume. So because at z is equal to 0 plane, it has got a mirror symmetry. Take it out, this part, and always do one thing before you delete it. Delete the mesh first so that it will become faster. Delete all mesh. Also quadrilateral, delete all. Okay, now modify, delete. So first what I'm doing is z is equal, see anything, see when you are applying symmetric condition, suppose now I want to apply a symmetric condition at z is equal to 0 plane, that is xy plane, then I'm allowed to model the problem only x greater than equal to 0. So that means only z greater than equal to 0. Only on this I can use this one, that's all. I cannot use this part. Whenever you apply symmetric condition about any particular plane, in this case I want to apply z is equal to 0, my model has to confine to only z greater than or equal to 0. That is the reason, because of that reason I am deleting this part. Gone. Okay. The next what I do is here, since I think some people are asking questions, I will come to the questions at the end. Okay, I'm not able to hear their questions for the time being. I'm not answering your questions. I will focus at the end. So this is done. Next, also there is a anti-symmetry. That is, what I mean is physics, volume current. You see here. Okay, focus on this part. Whatever current is coming here, it is going in this direction. It is at y is equal to 0 plane, there is a anti-symmetry. So I will apply anti-symmetry at y is equal to 0 plane. So again, because I want to apply at y is equal to 0 also anti-symmetric condition, my problem must be only in the region y greater than or equal to 0. So modify, delete volume. Now this time make it volume here. So what I do is all this part, they can go. I should not have. Remove this. Okay. Gone. Next, I want to apply one more, because if you see x is equal to 0 plane also, that is yz plane, again you got an anti-symmetry, then we will use that anti-symmetry facility, then delete volume. So your model has to be x greater than or equal to 0. So that's why these parts, they have to be deleted. Done. So now you got only 1/8 of the model. So in the similar way, you have to do for this box also. Okay, geometry, first intersection, cut the geometry with z is equal to 0 plane. Cut it. Okay. So once it's cut, modify, delete volume, delete this because you should not have that problem, because your problem has to be defined only at z greater than or equal to 0. Okay, done. Only half you got. Now we will do exactly the same thing. Geometry, intersection, planes. So now this time x is equal to 0, I take, intersect it, done. Then next again we do cut with plane, y is equal to 0 also will complete it, done. So next modify, delete volume, okay, make this as a block. So that means everything I selected first time. Next what I do is I will make this as a volume, only this piece and this piece, this piece. Second time selection means dehighlighting. So now all this green thing I want to delete. Okay, all the green thing part gone. Now this is 1/8 of the problem. Okay, 1/8 of the problem. Then what you have to do is you have to go to physics, symmetric condition. See here you say symmetric, x is equal to 0, I got antisymmetric, y is equal to 0, antisymmetric, at z is equal to 0, I got symmetric. Now say okay. Now can you see this yellow line, the yellow color indicates that those are the planes which are lying on the plane of symmetry and antisymmetry. Similar on the coils also. Okay, so now this problem represents the full problem that what we solved before. Now I will bring up that symmetry thick. Okay, one layer. Okay, this one will open this stuff. Now this is the problem, just 1/8 of the model. Now to solve this problem, let's go and see what is the requirements of the computer. Okay, problem size. So I exactly use the same element density. Okay, I copy this stuff and put it onto the paint so that you can see it better. Okay, here. Okay, see here. Here, this problem I'm using only 9,000 elements. Previously, if you remember that full model, I used 72,000. I think that they are here. Okay, 72,000 we have used. This is 9,000. This is 72,000 divided by 8 will become 9,000. Now the matrix equation is close to 19,000 matrix equations. Okay. In this, okay, then the hard disk requirement is greatly reduced, 5.2 GB plus add another 1.2, so 6 GB, maybe 7 GB hard disk is good. The good thing is, see this RAM. The RAM requirement is 1.37. That is, take 2 GB RAM. Okay, that is, where is 83 and this is 1.3. So the hard disk, the RAM requirement has greatly reduced. Okay, so that's what I want to bring it to your notice. Then let's see just the field values. You will see only one. Okay, 0, 0, 0, 30. Though the model is there 1/8, you can get the results anywhere, like in the anywhere full model. You can see the results. Analysis, field results. Let's take exactly scatter plots. Okay, like volume. Take this out. So let's take medium. I don't know why it comes. Okay. Okay, let's see here. Okay, make it. Okay. Okay, option put scale. Yeah, same thing, same field, 1.4980, that 14,980 Gauss. Okay, now what I do is now I will conclude this. because we exceeded the time. If I put the second layer, what will happen? I will bring that model. Okay, the 2-layered room. I put one more layer with a 10 centimeters drawn inside. Let's see. Okay, I will hide this surface because we don't need this for them. Okay, can you see here? See here, I got 2 layers there, and between these 2 layers, I used 10 centimeters. Okay, let's do this. Separation, I used 10 centimeters between the layers, and each layer is 1 centimeter thick. Let me do this from here to here. Let's take this part, copy. Let's put here. Okay, this is oh no. Okay, we'll do one thing. Just take this out. Cut. Okay, yeah. Okay, copy this. Okay, so now if you see, the distance is between the layers is 10 centimeters. Okay, with this thing, okay, let's make it all on. Okay, now I think one of the attendees, I think, asking question, can I use automatic? Okay, you can use automatic, and there's no problem. You can use automatic element generation, either 3D or 2D. You can use it. They don't have to exactly match it. Anyway, so here in this case, when I use 2 layers, the number of elements would be just double. 9,000 times 2. This is 18,000. The problem size in this case, the main important thing is the hard disk. This is 5.5 gigabytes of hard disk RAM. 5.5 gigabytes of RAM. That is the crucial thing. So still, 5.5 is not a big thing. So with this, you can solve a double layer model, and we calculate. Okay, what are the fields on this analysis fields? Okay, graph we will take. Okay, on the same, I took the same 350 mm. So this, okay, let's take that. Previously we got around 40 Gauss at this place. Now that 40 Gauss has reduced to 7.14 Gauss. And this part, it was something like 1.6. Now it has slightly increased. Yeah, it can happen. Someplace it's like a balloon. One side, once you push somewhere it will show up. So this is on this circle now. It has got the field is confined to anywhere between 2 points. Let's say 3 Gauss to 7 Gauss. And you can use different type of materials, higher permeable materials. You can bring down these values. So this is the 3D presentation. And suppose in your model, if you got a rotational symmetry in your model, or you are interested only 2-dimensional problems to solve, then you don't have to use AMPERES, a simpler program called a MAGNETO, our program that can handle problems very quickly. Okay, now with your permission, I will quickly close this the MAGNETO program. The MAGNETO program. Let's see. Okay, where is MAGNETO? Okay. Okay, MAGNETO. Let's open this. I will take a very small problem. Let's take this MAGNETO. So let's take this as the problem. Now this time I will take a inverse problem. Outside we got a stronger field. Inside I want a smaller field. So now you see here 0, the y-axis is the rotational symmetry, and this yellow color indicates. Okay, I will do one more thing here. Let's take this out. This segment is not needed. So if you see this, go to physics, material. The philosophy of Magneto and Amperes, the structure-wise, everything, menus, arrangement, everything is exactly the same. In this again, in this case, I'm using what kind of material? This steel mu metal I'm using in this. This is a can, a cylindrical can, and outside it has got physics. Okay, physics global setup. You see here Y rotational symmetric, and other facilities 2-dimensional, so you can use it, or X rotational or Y rotational. I prefer Y rotational. Physics, I used here in this case impressed fields. If you see here, my impressed field everywhere, there is an impressed field of, I think I took 5 Gauss. It can be anything, okay? I got 5 Gauss field is there. Once I have a cylindrical can, what is the field inside? And I'm using a 10 mm, same 1 centimeter thickness. Then what is the field inside? That is the problem. Now it is the reverse. Now you got fields here, 5 Gauss. 5 Gauss or whatever field, 1 Tesla or whatever thing, you got this field, and now inside field is a smaller field. For this kind of problems, finite element method is best suited more than the boundary, compared to the boundary element method. So because it is a inverse problem compared to the previous problem what we solved, analysis. Okay, to see the fields inside, it is comfortable for us. Let's see here. I want to draw this line, another region I'm creating, so that we can confine and see the fields here. Solution, solver setup, it is automatic, everything here. Of course, 2D models are at least maybe 1,000 times faster than the 3D models. That's all. You got the result. So this is almost like instantaneous. Let's go to B fields here. Let's get arrow plots in a region I am interested. Let's see. Okay, fine. If you see here in this region, what are my fields? Okay, let's make it bigger. Okay, 4 times. Oh, that is too big. 2. Okay, we'll do one thing. Delete all. Make it medium. Okay, now these are the field orientation. Outside is vertical B field, Y direction. Now here there is a angular direction here. The fields here at this place, you got increased 13 Gauss, but whereas inside it has got a smaller value. Let's see here. Okay, let's see. Okay, 1 Gauss here. Yeah, okay. Up to here, outside I think I used 5 Gauss. So here it come down 5 Gauss. Let's make it 0.2 Gauss. So 0.2 Gauss, 0.1 Gauss. So like that, you can see that means somewhere here the field is really small, like maybe 0.01 Gauss. Yeah, the 0.01 Gauss. Okay, this is 2D models. 2D models are they're so simple, very easy to solve, at least 1,000 times faster than 3D models. With this, I concluded my presentation. Now I go to the questions. The first question is: would you automatically meshing the? Yeah, you can use 2 layers, 3 layers, or anything, you can use automatic meshing is allowed. The next question, can one specify the B value of field in a contour plot? You can. The contour plot, you can select the contour plot. Maybe, okay, yeah. Any contour, you select a contour, and what is the range of that? Contour plots are given for every contour plot is given a range like somewhere 10 to 12. So along that line, if you traverse, we can select that plane and see what is the contour plot value, contour value. Can one specify the value in the contour plot? That's okay. Okay. Do you still have a 2-layer of 3D elements along the wall thickness in your model after the scaling up? Yeah, that's right. I'm coming to this question. 2 layers of 3D elements along the wall thickness in your model after scaling. Okay, yeah, I understood your question. Question is, I put the mesh where with a 25 centimeter thickness I put it. Then afterwards I scaled it up. Yeah, mesh won't get disturbed. Okay, next, what happens if you have only 1 layer of 3D elements along the room wall thickness for B of Z? Okay. So if you have only 3D elements, that is 3D elements in the volume, and you don't put 2D elements, no, program will not solve your problem, and you'll get. Yeah, there's no question of results. Problem, it needs. Whenever you are using, if you are using only sources like currents, only 3D elements, you don't need 2D elements. Okay, because the reason is in amperes, the current, any volume which carries current, we cannot put any material other than relative permeability is equal to 1. So once relative permeability is equal to 1 means you don't need 2D elements, only 3D elements. But if you are having a volume with only linear elements, suppose imagine that my walls are steel material where my relative permeability is suppose some 1000 and it is a linear material. In such case, you don't need 3D elements in that volume. You need only 2D surface elements only, you need it, and that way the problem will be solved very quickly. The reason is the matrix equation solved only once. There is no iteration involved there. You will get the, and many people, they do like this. What they do is first in this shielding problems, because this magnetic walls, they don't go into saturation because they are away from the coil, so they are still in the linear zone. What they do is they put a steel linear material, they will put it and solve the problem. Then once they do some experimentation, at the end of the experimentation, then they put the nonlinear materials. At that time, they put 2D elements and 3D elements, they will put it. Okay, next question. Contour 1, 2, 3, 5, 10. Okay, because for example, I think okay, I understood. Why not we go to the program and see? Okay, let's. Okay, I will come to this. The contour 1, 2, 3, 5. For example, I think it can be done. I will try it after answering one more question. Okay, can I check eddy current in the enclosure? Yeah, you can do that, but you have to use a different program called Faraday, our program Faraday. So that means what you are trying to do is you are saying that your shield has got not only this magnetic property, it has got conductivity, electrical conductivity. Yes, you can do that. What you have to do is, the program needed is program needed is Faraday, but it will take more time also. Like eddy current problem means you are specifying some frequency you have to specify, because if it is a static current, there is no eddy current. If it is a AC current, your coils carrying AC current, then you have to specify frequency. Then the model in Faraday, it will take a bigger space and bigger time. But once you apply the symmetric conditions, again, it will be possible to handle that kind of problems. Okay, now can I come to this? Yeah, I want to share my screen. Okay. Now I'm going to this contour thing. Okay, let's go to contour. Okay, let's see here. We can see in 2D itself. We can see option delete all plots. Okay, now let's see here. Contour. We'll take in one region. We'll take. So in this region. So okay, let me do this. Okay, colored, solid color. Apply. So this is the contours. Okay, now what we do is okay, lines. Let's go back to lines again. Colored lines. Apply. So these are the lines. If you see this, the red line indicates the brick red line indicates contour line is 63 to 59. Let me do one thing. Let's make it number is equal to 11. Then it will be apply. So also let's make it this user range also change it. Okay, 1 to 60. Let's see. I don't know. Let me see this. If you see this, if okay, this is okay. 1 minute. 1 to 6. 1 to 61. To 61. Yeah. Okay. 1 to 61. So 6.1. Okay. What is this? 11. Make it 10. Oh no. Maybe 9. I think something. I never tried this. Oh, okay, 10, 1, maybe 0. Let's try 0 to 60. 0 to 60. Try 10 first. Yeah, okay. This is if you try here. So now if you no, it's not great. Okay, let me try one more thing. I forgot. Okay, so okay, now you see here each line has got a range. This is on range. Okay, so suppose if you ask me to draw a contour line with one Gauss, suppose, I think that I cannot do it. I have to give a range. Like here, I say like in place of 0 to 1, I can do this. I can do. Where is that? Let me see here. So this is 0 to 1, 10 lines, 11 lines. Let's make it 2. Minimum is 2. 2 has to be there. Oh yeah, okay. Can you see that this line will be, the contour line will be anywhere between 0 to 1. I cannot just the lower limit and upper limit and lower limit. I cannot make it equal. Let me see here. One, I think it won't accept. I think. Let me see. Oh, no, it won't accept. Okay. So it has to be 2, minimum 2, and a range. You have to give a range. Now I say 5. Then it is 4. 4 to 5 range. So here 4 to 5 range is this is 4 to 5 range. Okay, but here, yeah. Okay, sir. That is my answer. Let's go back to question session again. Maybe okay. Stop sharing. Okay. Any question? Okay. If ampere is not calculated current in steel room, then will magnetic will minimize if you use one on magnetic. Then will the magnetic field be minimized if I use non-magnetic steel room? Okay. If the amperes is not calculating the current in steel room, will the magnetic field will be minimized if I use non. Yeah, actually it's like this. The amount of eddy currents are produced in the steel room, they are very minimal, and also those minimal magnetic fields, eddy currents, they produce very small magnetic fields outside. The thing is like this. The magnetic field you are seeing outside the walls, see, due to two things. One is leakage. The second thing is, if the eddy current, whatever eddy currents produce, that magnetic field also we should add it, but that will be very, very small. That's why most of the times the shielding for the MRI applications, our customers use only amperes. The Faraday they did not use, but sure, you should use. You can use Faraday also. There's no problem. And Faraday has got a switch. If you want to use it as amperes, you can use it as ampere. That means make the frequency is equal to 0. Static case, it works like amperes. But suppose you feel that you want to use specify the frequency for the currents for the coils, you can specify the frequency. Then it acts like Faraday, and at that time, if your material carries only the magnetic part, no conductivity, then there won't be any eddy currents. If your material has got magnetic permeability and also electrical conductivity, it takes into account both eddy currents effects also it take into account. I hope I answered your question. Thank you very much for attending the meeting. If you have any other questions or any inquiries, you can contact us through our website. Thank you very much. Bye-bye.